Okay, what did you get? Okay. What did you get for the first one, formula? Good.
Plus HCl.
Okay, for these reactants, did you write the state? For example, solid, liquid, aqueous, gas? Did somebody write the state of this one? HCl is, hydrochloric acid is a mixture of HCl and water, so this is AQ. The water present, does the PbI2 dissolve in it or not? So it's solid. This is going to give hydrogen with iodide and lead with chloride. So let's do the lead with chloride. The lead with chloride is going to be PbCl2, and then the hydrogen with iodide will just be HI. Now PbCl2, is that a precipitate or no? Is that a precipitate or no? Yeah. This is going to be PbCl2 solid. HI? No. And so what did you get for the driving force? Did you get precipitation as the driving force? Precipitation, we saw lots of precipitation reactions the other day. And those precipitates were driving force. However, in this case, can we be sure that this precipitation is going to be a driving force here? No, we don't know, because why? Because if we read this left to right, we're forming precipitate here, but if we read this right to left, we're also, and so we need to figure out which way is downhill. So in order to figure out which way is downhill, we need to know which precipitate is more stable. So we could use things like size, and we can try this theoretically, or we could look at the experimental data. We could try theoretically using Coulomb's law, but let's try this experimentally by looking at the data. Here's lead-2 iodide. That's what it looks like, yellow solid. So what would we look for? Well, melting point's 1. So if we look at the melting point, what is the melting point of lead-2 iodide? 402 degrees C for PbI2. Well, lead-2 chloride is white. Lead-2 iodide is yellow. These are the white crystals of lead-2 iodide. And we look for the melting point, 501 degrees C. Well, lead-2 iodide has a higher melting point, therefore you expect it to have a stronger lattice or weaker lattice? Stronger. So if this is stronger, that means it's more stable. If it's more stable, it means it's lower in energy. So it looks like it's going uphill. This is more stable, this is less stable. We want to go downhill. That would be a driving force. But in addition to melting point, what else would we consider? We'd consider solubility. And so let's look at PbCl2. If I look at the solubility of PbCl2, it is 10.8 grams per liter. 10.8 grams per liter. if I look at the solubility of PbI2, we have to do this per liter, so times it by 10. If we times it by 10, it's 0.44 grams per liter. And so which one dissolves more? PbCl2. So again, we have this conflicting kind of data. Because if it has a stronger lattice, you'd expect it to be less soluble. And so we saw that the melting point of PbCl2 is 500. So this has a higher melting point. However, the solubility is much higher. And after, if you see that, then it requires more data and more study. We've got to figure out what's going on. And after you see that and figure it out, then you'll see that the most important is solubility. And the less soluble one wins. So PbI2 wins. It's less soluble and it's more stable. PbCl2 is more soluble. And so if we're looking at the precipitate, then it's no driving force. If there's no driving force, we expect no reaction, but is that the only thing we consider? No. And so this is advanced here. You'll notice in our Chem 4 book, we'll never have a scenario like this. In our Chem 4 book, we aren't going to have solids here, so we aren't going to have to worry about competing precipitates, Because in other words, we're making a precipitate, yes, but we're also destroying a precipitate. And so is it worth destroying this precipitate to make this precipitate? If the answer is yes, then we have driving force. If the answer is no, then there should be no reaction. We should just stay with this precipitate. It's more stable. But that's not the only thing we look for in a reaction. What else do we look for? Mm-hmm. Both HI and HCl are strong acids. And if you look at this chart, then which one's stronger? HI is stronger than HCl. So we're going from weaker acid to stronger acid. Is that going uphill or downhill? That's going uphill. We don't want to go weaker to stronger. But there's a trick. All these acids here, when you dissolve them in water, have the same strength. That's called the leveling effect. Go back. It's a leveling effect. And so all strong acids have the same strength in water. And so HCl and HI, it's a tie. They're equivalent. And so that's not really a driving force. And so this one's pretty tough to figure out because of that. So difficult. So we probably base it on solubility, and in that case, there's no reaction because PbI2 is less soluble than PbCl2. We could figure it out, but we have to use more information. And so what's the easiest thing? Well, a problem like this that requires more information is beyond the scope of Chem 4. And so you'll never see a problem like this in Chem 4 because they're going to try to make it easy, you know, or easier. Not necessarily easy, but they're going to try to make it so everything works out nicely. The problem is if everything works out nicely, you know, and you're never exposed to any difficult problems, then you sometimes can be misled into thinking that everything works out so nicely. You know, there are no complications. And so I want to talk about a couple of things. One, you know, there are some problems that we have to think more about than your typical Chem 4 problem of these, and we need additional data to. And two, there are some basic assumptions with our predictions. These are the basic assumptions with our predictions. One, we're dealing with reasonable concentrations, not overly concentrated, not overly dilute. Because if a solution is overly dilute or overly concentrated, it can alter what we end up getting. And two, the gases are reasonable pressure. If the gas pressure is extremely high or extremely low, that can alter our predictions as well and complicate things. So here, in this particular reaction here, I expect driving force. Do you see the driving force? So we're taking HCl, hydrochloric acid, EQ, and what's this called? AgNO3. AgNO3 is called nitric acid, or no, not nitric acid, silver nitrate. And so if we take these are both solutions, we're going to form this. What's this called? And this. Nitric acid. Now, is there a driving force for this? First, we look for our precipitate. Do we have a precipitate? Yeah, we do. And you go, okay, we got a precipitate there. That's all we need. Are there any other driving forces? Yeah, how about acid? Strong acid to weak acid. Is that the case? Stronger acid to weaker acid, HNO3 and HCl. Let's take a look at our acid chart. Which one's the stronger acid? HCl or HNO3? Looks like HCl. HCl is a stronger acid than HNO3. But all we have to do is we have to just realize that all we need is one driving force. So if HCl is stronger, we are going from stronger acid to HNO3, which is a weaker acid. But you got to know something about the strong acids, and that is they all have the same strength, so it's a tie. Actually, HCl and HNO3 are tied. Now the weak acids will have different strengths, but the strong acids will have the same strength in water. We'll come back and talk about that later. And so the acid doesn't really tell us anything, but since we got a precipitate, we expect driving forces present. And so, and that works out. At reasonable concentrations, it works out. However, if the concentrations are very low, we call it dilute, very dilute solutions, or very dilute concentrations of HCl and silver nitrate yield no reaction. And so even though we're mixing HCl and silver nitrate, nothing happens. Actually, this is a typo. Nothing happens because the concentrations are too low. And so, yeah, we predict we predict a reaction should occur, but if things fall outside our little window, then it's more difficult to predict. so we expect a reaction to occur here. But here, like silver chloride and HNO3, that's a reverse reaction here. Silver chloride and HNO3 is going backwards. So if it's downhill going forwards, then going backwards should be uphill. And so going backwards should be difficult. And so therefore going backwards we expect NR. NR stands for no reaction because we're going uphill. But when we combine silver chloride with hot concentrated nitric, then we get a reaction. And so things can change if the conditions change. So we just have to realize that what we're talking about are these types of conditions. Not only that, the other restriction here is that we're talking about a thermodynamic driving force. Thermodynamic driving force is, you know, which way is downhill, which way is uphill, that kind of thing. And so this is downhill also. For example, diamond is less stable form of carbon than graphite. And so to go from diamond to graphite should be downhill. That should be a driving force. It should just naturally occur, right? But the problem is this. Diamond is so unreactive that it doesn't want to convert into graphite. So even though it is downhill, nothing happens. And so, in other words, diamond is what we call metastable. That is, it's stable but not really stable. It's thermodynamically unstable compared to graphite. Graphite's a more stable arrangement of carbon atoms. However, it's too difficult to convert diamond into graphite because of the bonds. You have to break all the bonds and replace those with the graphite-style bonds. So it's not so easy to do. So the take-home point of this is that, yeah, we're making these predictions, but you have to keep in mind, you know, sometimes the predictions aren't perfect. And that's it. So this one is advanced because we need to know, you know, how does PbI2 compare to PbCl2? And therefore, we probably look it up online, or we could try theoretically, you know, what makes a stronger lattice in theory. But in other words, it turns out that this one has no reaction. So we're going to take a look at some additional examples here. All right, let's try this one. Calcium chloride and potassium fluoride solutions react to form a precipitate. Here it says it is not necessary for you to identify the precipitates formed in questions 23 through 26. But that's too easy. You should be able to tell me what the precipitate is in this one. So give this one a try. After you do that one, you could try the next one.